talk a little bit about enthalpy and why it turns out to be a very important variable for open flow systems and thermodynamic analysis of control volumes. So up here you see a pretty nasty looking expression, and I want to reassure you this is nothing more than the first law of thermodynamics, but it's been expanded and written in a very mathematical form, okay, using something called tensor notation. And if you've never seen this before, don't worry. It's likely you won't be tested on this in this class, but I think it's good to just get a look at this right now before you may encounter it in more advanced classes. If you're interested in learning a little bit more about this particular type of notation, i.e. the subscripts, just look. You can Google tensor notation, or see the book Incompressible Flow by Panton. Okay. So anywho, this entire first line up here is an expanded form of the first law. Okay, and it's been specifically manipulated for an open thermodynamic system. So starting from the left over here, I've got this term, the time rate change of this integral over the entire control volume of the product rho little u dV, big V. So this is the V is for the volume, the control volume, differential volume. The rho is the density of our substance, and U is the specific internal energy of the substance, which could be a function of both space and time, obviously. So just this integral right here, I'm summing over all of these differential volume elements, this product rho U, and the product rho U gives us the internal energy per unit volume, okay, within our control volume. So this entire integral is going to give us the total internal energy of our system. And I'm curious what the time rate change of the internal energy is. And we should know from previous lectures on or exposure to the first law of thermodynamics that the internal energy of a system can only be changed by several different ways, either heat transfer or work transfer, or by a mass transfer into or out of the system. Okay, so we've got one side of the first law. Now, the second part I'm going to come to in a minute, but let's skip over. You'll see that so the time rate change of internal energy is equivalent to a term that you've already seen, the heat transfer to the system. So I've written this as Q dot total. And I haven't expanded it in anything more mathematical than just this symbol here, because it could come in several different forms. So it could be volumetric. This could be due to, say, radiation, or maybe we'd like to model a chemical reaction occurring internally as a volumetric heating source. Or it could come through thermal contact at the boundary of our particular control volume. Okay, so both of these are included in this heat transfer term. The second term over here is actually representative of shaft work. So this is one of the two types of work that you'll likely encounter in this course. So shaft work, and then the other term, which is really the focus of this entire video. So the shaft work I've broken up into something a little bit more fundamental that you probably haven't seen before, but it's nice to get an idea of what the shaft work actually means. So here I've written the summation over J. So J is going to be, say, J discrete points over our control volume where shafts may enter the system in order to transmit work into the system or remove work from the system. So a discrete summation, and then at each J point, I'm going to be integrating over S sub J, which is going to be the cross-sectional area of the shaft. And what I'm concerned with within that cross-sectional area is the shear stress distribution on the cross-section of the shaft. And I want to take the product of that shear stress and then also the radial distance from the center of the shaft to where that stress is acting, and then also the angular velocity of the shaft itself. And so the product of these three with the differential cross-sectional area element. Okay. Actually, just to take a small side note, because I think it's better if we look at the units to make sure that we're dimensionally consistent. Here we've got energy per unit time, which is actually the same as work per unit time or power. But let's look over here for a side note for a second. So work, as you should recall from Physics 1 or mechanics, is simply a force that moves a substance or an object through some kind of distance or displacement. Now, if I just multiply by unity, haven't changed anything, I'm multiplying this expression by area over area. Rearranging, I get force per unit area is a pressure, and a distance times an area is a volume. So work can also be expressed as a pressure, which is acting or moving something through a volume. Furthermore, so power is the time rate change of work, so work per unit time. So power can also be expressed as a force times a velocity. So if I'm pushing on an object and it's moving at some speed v, I'm actually transmitting power to the object. And then also pressure times a volume flow rate, so the rate at which it's changing volume. This is also a power or a time rate change of work or energy. So let's check the units here. So we've got tau sub j, which is the shear stress distribution on the shaft. That's essentially stress and pressure, the same thing, a force per unit area. So if I take this and multiply it by a differential cross-sectional area element, I'll get a shear force distribution on the shaft. And then that shear force distribution would be multiplied by this inner product, which is the radial distance from the center of the shaft times the angular velocity of the shaft, which is going to give me a tangential velocity around a circle whose radius is r bar sub j. So again, the outer product is going to give me a shear force times a tangential velocity at the for this product at the innermost term in this expression, and a force times velocity gives me a rate of work or power term. So this is this integral right here would be the rate at which work is transmitted to the system at given shaft j. Okay, and then I'm going to sum that over all the shafts that may be entering or exiting the system. Okay, so that is our W dot shaft term. So we've covered Q dot, W dot. Now this last term may be less familiar. And along the same lines here, what I'm trying to do is manipulate some of the variables we know into a form where we get a rate of work, okay, or a rate of change of energy. So in parentheses, I've got this expression, a pressure, so say my fluid is exerting a pressure on the control surface, and maybe that control surface is deforming, or maybe there's fluid moving through the control surface. And that fluid that it's moving has some velocity associated with it. So this product is a force per unit area, the pressure or stress, times a velocity, which would give me a force times a velocity per unit area, or power per unit area. And then over here, this term is Ni ds, which is, the Ni is just a unit vector associated with the entire surface, and so each portion of the surface has a vector associated with it, which will tell me essentially what the geometry and relative orientations of the surface are. So it's unitless, but NIDS is going to give me the differential surface area element on my control surface. So I get a power per unit area times an area, okay? That's going to give me a differential unit of power, and I'm going to sum this up over the entire control surface, okay? So this is going to give me a term which is relating the flow work, like I've listed here. The flow work, pressure work, surface work, or boundary work, all these terms are synonymous. That's associated with the fluid or substance pressure within my control volume, either displacing fluid that's surrounding it, okay, so it's doing some work, or the fluid may be flowing into the system and doing work on the system itself by the same means. It's at a pressure and it's displacing some volume of fluid that's in our control volume. An alternate way to look at this is if we regroup things and have the pressure by itself, and then have these last three terms together, this product, V, I, Ni, ds, is actually a velocity and an area. If you work out the units, you'll get an area times a distance per unit time, or a volume per unit time. So the product of these three is actually a volumetric flow rate. And like we mentioned before, pressure times the volume flow rate is going to give us a rate of work or power. Okay? So again, this is maybe a new term for some folks here. And this is very important for open systems, because imagine any open system has at least a single inlet or a single outlet, or possibly more. And say for on an inlet side you have fluid that's rushing into the system. So upstream fluid is actually more or less acting like a piston to displace fluid downstream in our system and doing work on it. Whereas if I have an outlet pipe, there's fluid in my system that has to do work against fluid downstream by using its pressure to displace a certain volume downstream. So this is very important to understand this intuitively. Now on the second line here, again, just done a little bit of manipulation. I'm going to actually take this term, multiply it by unity. So it's probably best if you do it yourself first to see if you can come up with this expression for yourself. So you may want to pause for a second and see if you can get to this line here. But as far as multiplying this first term by unity, I'm going to do multiply this guy by density over density. So rho over rho, and then bring it to the left-hand side of the equation. And ultimately, we should end up here on this second line. So this first term here, which I haven't explained these two quite yet, but I will in a minute. This first term stays the same. Now, the second term here, if you just look at the structure of this term, it looks very similar to this last flow work term over here. And I can simply do a little bit of algebra and manipulation, factor out this product, rho v, or vi bar, and what I have left over is u plus p over rho. And then left over here is ni ds. So that was, all these were in common with both terms. And this is equivalent to the remainder of the terms on the right-hand side of the equation, the total heat transfer, and the total shaft work into the system. So before I move on to talking about why this term in brackets is so important and relevant for open flow systems, I want to talk about these first two terms briefly. So initially we had this time rate change of an integral, okay? And so the integral of rho u dv, which we said was the total internal energy of the system, for deformable systems, so deformable solids or fluids, things of that sort, the limits of integration we can actually change because we don't have a fixed geometry. And that's when we need to use some pretty fancy mathematics in order to take a derivative of an integral with changing limits of integration. You may want to go back to calculus to review this. I believe it's called Leibniz's rule for moving a derivative under the integral sign. You can Google it as well. But essentially, because of the deformation of the fluid, we can break this derivative of an integral up into two terms. Okay. For those of you that have taken fluid mechanics, this may be familiar. This particular mathematical operation is seen pretty often when you go over Reynolds transport theorem in fluid mechanics. So this derivative of the integral breaks down into two terms. We have one term that describes the time rate change of the internal energy per unit volume within our control volume, whereas the other term over here describes the rate at which internal energy fluxes through the surface. So the total flux of internal energy through the surface. So this one is pretty easy to see. You've got a partial derivative with respect to time of this product, rho u, which is the specific internal energy times the density. Together they form the internal energy per unit volume. And this whole thing is integrated over the entire control volume, so the same term comes down here. Whereas this term, we've got this product, rho v, bar. For those of you that have already taken fluid mechanics, this should look familiar. This is actually the mass flow rate per unit area, okay? And then again, NIDS is a differential area element, so the product of these two is actually a mass flow rate. And then U we have is the specific internal energy, the internal energy per unit mass. So the product of the mass flow rate and the specific internal energy is going to give me a time rate change of internal energy due to bulk flow or advection into and out of the system. So again, as I combine this last term, the flow work term, with this internal energy flux term, and then move down here to the second line, and again, rearranging, doing a little algebra, we get this combination internal energy U plus P divided by rho, so the pressure divided by the density. This is what we define as H, or the enthalpy, the specific enthalpy of the system. And again, just the sum of the internal energy and this term right here, the ratio of the pressure and the density. Now, because the density is inversely related to the specific volume, 1 over rho is equal to V, little v, the specific volume, we can also write H as U plus PV. So ultimately, instead of keeping these two terms separate, for open system analysis, what we do is we combine them together into this one variable. And so this whole term right here would be rho v H NIDS, and altogether it would represent the total enthalpy flux for the system. And ultimately, the first law would become the time rate change of internal energy within the control volume, plus the total enthalpy flux out of the control volume must be equivalent to the total heat transfer and the total amount of shaft work entering or leaving the system.
The Teaching Center, UF's Learning Resource Center.